Thank you very much. So first, let me thank the organizers for selecting my talks, and also for selecting actually 4 talks in the science program about the young eruptive stars. I think there is a very good reason to do that. These objects are potentially very important for the early stellar evolution. They are enigmatic enough, so really basic fundamental things we just don't understand about them. They are bright, so it's good for our instrumentation. And I think this is enough reason that they are selected. So we have a V900 Mon, which is one of the relatively new F-Orionis type stars. It was discovered in 2009 by the British amateur astronomer when he realized that this very nice reflection nebula that we see here in Monoceros, it was not present or only very weakly in the Palomar prints in the 90s. When we collected, or when in the literature people collected actually earlier historical photometry, it became clear that the brightening of this source happened somewhere between 1990 and 2000. The increase was quite substantial, this 4 or 5 magnitudes, and the spectrum of this object, which was observed by Stefan Krauss actually, shows a striking similarity to the spectrum of F-Orionis. So no doubt that this is an F-Orionis type star. It has all the criteria for that. The only disadvantage of this object that is relatively far at 1.2 kiloparsecs, so it's not that easy to observe. Anyway, why do I like this object and why do I give a talk about it? Well, the reason comes from another project. In 2008, we observed another outburst. It was a smaller style and smaller scale outburst. It's called AX Lupi. But still, we found that some of the crystalline silicate particles, which was originally amorphous, they became crystalline. And it was due to the heat of the outburst. It's just warmed up the inner disk. But then I started thinking, why don't we see similar crystallinity for crystal formation in the F-Orionis type object, which are much bigger, you have a much more heat, you have a much more energetic irradiation. So you would expect that a large area of the disk becomes crystalline. And we don't see it. So you can imagine, when I looked at the MIDI observation of this new guy, the V900 Mon, and compared it with the blue one, which is the spectrum of the solar system Hale-Bopp comet, with a very high crystallinity ratio, and the two really showed a beautiful match, then I said that, okay, now we got it. This is the guy where we have the crystalline silicates. It really became a kind of passion for me to find the guys which have the silicates. So when I saw this plot, I did 2 things, submitted a Matisse proposal just to confirm this discovery, and contacted the Nature editors. So then I got the Matisse proposal, not the Nature, and these are the summary of our Matisse observations. It was 2 snapshots at the end of 2019 and early 2020. And since I knew that I need to present these results at the Sharpest Eyes conference, then that's why we also observed it at other Sharpest Eyes events, like the VLT Muse and with the ALMA. The results are summarized here. First, look at the bottom line, which are our Matisse results. In the L band, both in the L band and the M band, the source is very well resolved. So it's clear that it's not point-like at this wavelength. The L band is just a kind of featureless spectrum. We don't see, and it's quite red spectrum, it's increasing. In the N band, as if you would see some deviation from a linear increase, so probably there is a weak silicate feature in that. We will study it a bit further. These are the closure phases. Well, with this accuracy that we have, it seems that we cannot really say about anything about the asymmetry. With the ALMA on a larger scale, it's in a paper published by Kospa et al. And Takami et al. We saw, I don't know what is this little thing here, we saw a large-scale CO outflow with a nice cavity, and the disk. The disk properties are quite unusual for a young star. So it has a small radius of only 22 astronomical units. And for this small radius, we have a huge mass, around 0.3 solar mass, which is really a very massive disk. So no wonder that it can be gravitationally unstable. And that was the conclusion of Agnes' paper. But we are most interested in the silicate feature, whether we see the crystalline silicates or not. So the left-hand side, these are the 6 Matisse baseline spectra. And it's interesting that they are not completely parallel. So here it shows a quite steep increase, while other baselines don't show it. At the higher flux, these are the short baselines, so they represent the large-scale emission. At the bottom, these are the longest baselines, which just sample the central area. And here in this cartoon, you see the same, that those spectra which cover a larger region, something like 30 AU, they show a kind of trapezoidal shape. But when we go more inside, in the light blue, then somehow this peak disappears. And when we go really to the inside, then this part becomes even negative. So what it is, of course, I was happy looking first at the central part because it looks similar to the Matisse, to the MIDI observation. So I thought that maybe these are my crystals. But what one can really conclude from this, that there is a radial change of the crystalline properties in the system. This is just a zoom on the same thing. And here I compare the intermediate and the small scale spectra with the one on the large scale. So this is always just a copy of the large scale. And something is missing from here. If I plot here the difference between the two, then the missing flux somehow peaks, in the negative sense, close to 10 micron. Maybe this is not a correct explanation. But I just fitted it with a ISM type amorphous extinction curve, which peaks at 9.7. And actually, this is a possible explanation that what we see, this is not a silicate feature, not a crystalline silicate feature, but we have some absorption toward the source. This absorption, interestingly, very, very confined. It just covers the central part of the system, not the whole disk, just really toward the star in a very small area. It's a few astronomical units, maybe 1 or 2. And this is the strongest one. But the other part of the disk is uncovered. If we estimate with this interpretation how deep is this absorption, we get something like 10 magnitude. So that's a lot toward the star, but only toward the star. So, of course, there is another possibility that what we see here, this is maybe a companion sinusoidal signal. This we need to check still a little further. Why it's interesting, actually, this little absorption feature? The main reason that previously, from the ALMA images and also from our Matisse observations, we concluded that the disk is closer to pole-on than to edge-on. So if you have an absorption feature toward the star in a close to pole-on system, it must be really out of the disk material somewhere. So what is it doing there and how could it happen? Maybe it's some streamer or maybe some infalling material or maybe some ejected material which just leaves the center of the pixel. Let's check for that. We have the Muse observations with a very high spatial resolution in the center. So we looked whether we see some jet or ejection outflow signatures. These are these forbidden optical lines. But the result is quite simple. We don't see any toward the star. So actually, no jet, no material which is coming toward the star in the present outburst. But if you look at the larger scales, then in an H-alpha image, we could identify several blobs, 3 nice little blobs, which really line up with the star, and this is also the direction of the ALMA outflow. So it seems that at earlier times there was some activity, some matter ejection activity, but not in the present outburst, because if you calculate some time scale between the star and the first node, it's more than 100 years with some reasonable assumptions. So there was some activity before the present outburst, but this is not related to the present outburst. We also did some simple analytical modeling of the spectral energy distribution of the source. With this steady optically thick disk, you can see the Hartmann basic books about it. And the result, I need to remove it again, that the luminosity is something like 400 solar luminosity. The accretion rate is 5.10 to the minus 5, AV 10, and the outer radius of this disk, the accretion disk, is relatively large, maybe unusually large. Finally, this is a plot that there was a survey of Agnes Kospel actually looking at with Vizir at the whole system to explain this trapezoidal silicate feature that we saw at larger scale. This is the source, which is here put into context compared with other stars. It seems that most of these are all fjords. It seems that for fjords is quite typical what we see here, but we don't know the reason. Why is it a characteristic of fjords? But the most important and really the sad thing that we don't see any silicate feature in this fjord collection. So as a summary, we studied with the sharpest eyes on the sky the newly discovered V900 Mon source. And our main results that in the inner part we see a classical accretion disk with a relatively large size and large extinction. On larger scales, ALMA show a relatively small but very, very massive big disk. We may see some out-of-the-plane absorption component. We have no idea about the origin. We discovered some new jet nodes, and no crystals still. Many thanks for your attention.
Okay, thank you very much, Peter. Are there any questions? Yes?
So you mentioned the nodes. From the nodes, can you derive how often outburst happens? If you can derive the time each node to be...
So that the time between these nodes, you mean?
Yes.
It's something like the order of 100 years. So I calculated that between the star and node 1, this is about 100 years dynamical time scale. So it's a few hundred years what we see here. So there was activity in the past millennia.
But does that mean this star have one outburst every several hundred years?
If you interpret a jet node like this, then yes, but of course, many young stars have jets, so if those are all fewer outbursts, I doubt.
Okay, thank you. Any other questions? We haven't got anything online. Oh,
okay.
Yes, please.
Yeah. And I want to know why you explain the change of the 10 micron spectral feature as due to absorption. Is it possible to be the change of mineralogy at different regions of the disk?
In principle, it's also possible, of course, that a really radical change in a mineralogy is there. But yes, we cannot exclude it would need a detailed modeling. Unfortunately, to do a real reliable mineralogy fitting with the different components, you need a relatively high signal-to-noise of the spectrum, and I'm not sure we have that. But this is a possible explanation, of course.
Yeah, but if you produce a special absorption at some wavelengths, you still need a very special mineralogy to produce an absorption, right?
Yes, I just fitted it with a the most common interstellar type amorphous submicron grains. So, but you are right.
Okay. I want to know whether the baseline maybe have some impact to your derived dust features. Because your spectrum is not very long, right? So the baseline is slant. So how did you determine the baseline to derive the dust feature?
Okay. Well, it's just a simple linear fit. Basically, you connect the region around 8 micron, 8.5, and something like 12.5. So that region where the multispectra are still reasonably good.
Okay.
So that was not a modeling or something. It was a linear continuum. Yes.
Great. Okay, well, we're out of time, so let's
Okay. Thank you.
Thank you.
Yeah. Let's thank Peter again.